Hello everyone, this highlight video is going to be on resonance theory. So this is going to tell us about the situation where more than one Lewis structure is possible. So let's look at an example so we can explain what this means. Alright, so let's just work out a Lewis structure first off. Okay, so here's our structure, or here's our formula, CHO2 minus. Okay, so first step, we calculate out the number of valence electrons. So we have 1 carbon, 4 electrons, we have 1 hydrogen, 1 electron, we have 2 oxygens. Each of those is worth 6, so we have 12 electrons, and we have a minus charge. So what do we do with a minus charge? We add 1 extra electron. All right, so this gives us, what's the total? 4, 5, 17, 18 valence electrons. Okay? So we're talking about organic molecules, and so the carbon is going to be placed in the middle. Oops, we have an oxygen. I'm just going to go ahead and draw the bonds between these atoms, and oxygen. And the last thing that we have to place on here is the hydrogen. All right, so it's a little hard to tell where to put it, but let's say we're going to put it on the carbon. Okay, so 2, 4, 6 electrons we've used. We have 8, and we have 12 more to go. All right, so let's start by putting them on oxygens. There's 2. We can go symmetrical here. 2, 4, 6, 8. All right, so this should be a total of 18 electrons. Does this structure look good? No, because the carbon right here still only has 6 electrons around it. Right? So we want to have that carbon to have a full octet. So we have 2 choices here. We can use a pair of electrons to form a pi bond or a double bond, but we could use a double bond from the top oxygen, or we could use one from the bottom one. Okay, so let's start out by moving this pair down here, and we're going to draw the new structure. So now we have a double bond and a single bond. We have 2 non-bonding electrons on the top oxygen. We have 3 pairs of non-bonding electrons on the bottom oxygen. So is this a finished Lewis structure? No, not even yet. We still have to position the minus charge. All right, so if you remember back on the last highlight video, we saw a situation where if we have an oxygen with 1 bond and 3 non-bonding electrons, it will have a minus charge. So we could easily calculate formal charges to locate that. All right. What if, though, instead of using the top electrons, what if we used the bottom electrons? Right? That would give us a slightly different structure. Because our double bond would be to the bottom oxygen. So now the top oxygen has 3 pairs of electrons with the minus charge, and the bottom oxygen has 2 non-bonding pairs of non-bonding electrons and a double bond. All right, so what's the relationship between these 2 molecules? Well, if we compare them, we could see, number 1, they have the same molecular formula, right? Are they the same or are they different? but these are different. Okay, because the oxygen that has the minus charge is a different oxygen. So if they have the same molecular formula, but they're different, that would suggest that these should be what? These should be isomers. However, for them to be isomers, these two molecules would have to be discrete. All right? And I'm going to show you now that in fact they are not. These two structures, I've just redrawn them on this slide, are referred to as resonance forms or resonance hybrids. Okay, we can show how one of them could convert to the other. So if we take a pair of electrons here and we move them down to form the lower double bond, these electrons move up onto the top. That would form the structure on the right. And likewise, we could go backwards if these go down here and these go up here. So in these cases, these arrows are showing the movement of electron pairs. All right, but what's been discovered over time is that neither of these structures really are accurate representations. All right, and the true structure is actually a composite of both of those, and that composite is referred to as the resonance hybrid. So instead of having electrons going back and forth, those electrons are simply spread between the two oxygens. So we could draw what would be what we might call the true structure, and it would look like this. All right, so in the left structure, the bond between the carbon and the upper oxygen is a double bond, and over on the right side it's a single bond. So what we do is we draw the second bond as a dashed line. And so this refers to that dashed one is a partial bond. Okay, and the bottom one would be a partial bond as well. We notice that the left structure has a minus charge on the lower oxygen. The right one, it's neutral, so it would have a minus 1/2 charge on this oxygen and a minus 1/2 charge on the upper oxygen. So the true structure has the minus charge and the electrons evenly spread between these two atoms. This concept of resonance describes a delocalization, we call it, of the electron. So it's delocalized over two different atoms. And the hybrid is going to be more stable than the individual resonance structures, and it's said to be resonance stabilized. One last important concept for this slide is this type of arrow right here. So this double-headed arrow is always reserved for resonance. Okay, and other kinds of arrows we've seen, if we see an arrow like this, all right, that refers to equilibrium. That's where the species are going back and forth, converting and reversing. So we don't want to mix up these two types of arrows. All right, so let's look at important principles of resonance theory. All right, so in resonance theory, resonance structures differ only in the positions of the electrons. Okay, the atoms can't move. Resonance structures are not real, so the individual resonance structures are not real. The true structure is the hybrid. Resonance structures are not in equilibrium. Okay, the electrons are just spread, and the resonance structures are not isomers. Before we move on, take a look at this problem and see if you can determine which pairs of molecules represent resonance structures. All right, so let's broaden our understanding a little bit more. Let's look at three generic situations where resonance is observed. So notice in all three of these, A, B, and C, what I've done is I've listed three atoms, X, Y, and Z. And these atoms could be any of the atoms that we routinely study, typically on the second row of the periodic table. So type A will be where we have a non-bonding electron pair on an atom adjacent to a pi bond or a double bond. All right, so in this case, I'm going to put a non-bonding pair here. So we have a lone pair on an atom next to a double bond. All right, so in this case, what can happen is that these electrons can move toward the double bond, and that Y group, if it had a full octet of electrons, it depends on what atom it is, couldn't hold any more electrons, so it's going to push its electrons over to Z. And this creates a resonance contributor. Now, where the double bond is to X, and the non-bonding pair of electrons is on Z. All right? So in some cases, this X and this Z group could be charged, or some types, depending on the atoms, it could be neutral. So we've seen one example already, and this was our structure like this. Okay, so in this case, we had non-bonding electrons, let's just pick out one of these, on an atom next to a pi bond. And so we can generate another resonance form by moving the electrons toward the pi bond, and the pi bond electrons move on to that adjacent atom. All right, so that's one example of type A. Type B is a situation where we have a positive charge on an atom adjacent to a pi bond. Okay, so in this case, we're going to just put a plus charge on X and our double bond going between Y and Z. So in this case, the way we generate our other resonance form is for the electrons in the pi bond to move toward the plus. And if that happens, our second resonance contributor will have the double bond between X and Y, and the plus charge is now left behind on Z. Okay, so we'll see some examples like this as we move forward. The last example, which we won't see many examples of until probably next semester, but I'll just give you a heads up, is when we have an unpaired electron on an atom next to a pi bond. So we're going to put a single electron here, and between Y and Z we'll put a double bond. And the way we would draw these is this electron would go here, so this single-sided arrow is the movement of a single electron. So this is the movement of one electron, this is the movement of two electrons. So we would split the pi bond, this one would go over there, so those two come together to form a new pi bond. This electron goes over to Z, and we generate a new resonance hybrid, this time again with the double bond between X and Y, and the non-bonded or the unpaired electron on Z. All right, so notice in all three of these types, we have either a non-bonding pair, a positive charge, or an unpaired electron, which is called a radical, on one atom and it's adjacent to a pi bond. So in resonance, we are showing the delocalization of electrons using double bonds. Take a look at these problems and try to determine whether the structures would belong to a type A or type B. Remember, type A has a non-bonding pair and type B has a plus. Another concept is that not all resonance structures for a given molecule are created equal. In fact, not all of those resonance structures are going to be equally stable. All right, so we can follow this general rule that says that a more stable resonance structure is one that has more bonds and fewer charges. Okay, so let's look at a couple of examples here. So our top structure there, this carbon-oxygen double bond with a hydrogen next to it, is called an aldehyde. All right, we only have one double bond, so the only thing that can really happen is that the electrons in that double bond could be moved to one of the two atoms. So let's move them up onto the oxygen. If we do this, it gives us a new structure. That now has only one bond to the oxygen, but it has 3 pairs of non-bonding electrons on that oxygen. Okay, we've seen that situation before. We know that the oxygen will have a minus charge. The carbon, though, lost some electrons, so it's going to have a plus charge. All right, so these two molecules are related only or differ only in the positions of their electrons. So they are, in fact, resonance contributors or resonance structures. So let's determine which one is more stable. All right, so let's follow this rule. The more stable one will have more bonds and fewer charges. Okay, so that's pretty easy, right? This one over here has more bonds, it has an extra bond, and it has no charges. It's all neutral, whereas the one on the right has fewer bonds, and it has a minus and a plus charge. All right, so the more stable one is going to be represented more in the true structure. All right, so the true structure is a weighted hybrid of the individual resonance contributors. The true structure will look more like the structure on the left because that's more stable, but that doesn't mean that the structure on the right will not have some contribution. So we could draw the resonance hybrid looking something like this. And I'm going to go ahead and draw the double bond because that's by far the more stable structure, but how we can represent this is that the oxygen will have some greater amount of minus. We can draw this as a delta minus, a partial minus, leaving the carbon as a delta plus. So essentially, our drawing of the resonance contributors is an example of demonstrating that this is simply a polar bond. Let's look at the bottom structure. So let's see if we can draw some resonance contributors for that structure. When we look at the structure, we notice that the nitrogen has only 3 pairs of electrons around it. So it only has 6 electrons. Right? The carbon has 8, the oxygen has 8. So if we can come up with a structure that gives that nitrogen a complete octet of electrons, it's also going to be more stable. So one way that we could do that is to take this non-bonding pair on the carbon and push it down to share it with the nitrogen. If we do that, there will now be a double bond between the nitrogen and carbon, while we still have the double bond between the carbon and the oxygen. The nitrogen still has 2 pairs of non-bonding electrons, but the carbon has no non-bonding electrons and the oxygen still has its pair. All right, so our new structure, or our resonance contributor, still needs to have the same charge, right? So where is that minus charge going to go? All right, so let's try a formal charge calculation. Let's do it for this nitrogen. So the formal charge equals the valence of nitrogen, 5, minus the number of non-bonding electrons is 4, plus half the number of bonding. There's 4 bonding electrons in the double bond, divided by 2. 5 minus 6 equals minus 1. Okay, so in this resonance contributor, the minus charge will be now on the nitrogen. Okay, I'm going to draw one more example here, and I'm going to show you how we could actually move more than one pair of electrons in a row. So what we're going to do this time is we're going to take this pair of electrons. It's going to move down between the nitrogen and the carbon to create a triple bond, but that carbon can't hold any more electrons, right? It can only have 8 electrons around it. So it has to give up a pair of electrons, and it's going to give it up to the oxygen. Notice that the arrows that I'm drawing to show the movement of electrons always originate with a pair of electrons, and they're always either going to form a new bond or to be located on another atom. All right, so now this nitrogen has a triple bond to it. Carbon has a triple bond and a single bond. And the oxygen has 3 non-bonding pairs of electrons. Okay, so now where's the minus charge? Okay, well, we've seen this kind of oxygen before, and so the minus charge is going to go on to the oxygen. Can we decide which of these 3 resonance contributors would be most stable? So let's follow the rule above. We're looking for structures with more bonds and fewer charges. So each one has the same number of charges, right? They all have a minus charge, and in fact, each structure has that minus charge on a different atom. What about the number of bonds? Well, the 2 structures on the right, the middle and the right, both have 4 bonds. The one on the left has only 3. So this one here is going to be the least stable. Essentially, we could also say it's least stable because the nitrogen does not have a complete octet of electrons. Can we tell between the 2 structures on the right, the middle and the right, which one is more stable? Well, not really based upon the rule up above. So I'm going to give you another rule, and that is if the bonding and the number of charges is the same between 2 resonance contributors, or if all else is the same, the structure that has the minus charge on the more electronegative atom is going to be more stable, Or we could see a situation where there's a plus charge, and that plus charge would be best held by the more electropositive atom. So in this case, which of these two is going to be more stable then? We have a minus charge on nitrogen or a minus charge on oxygen. All right, so the more stable one is going to be with the minus charge on oxygen because oxygen is more electronegative. The next slide writes out that rule. It says, for all things being equal, the more stable resonance contributor will place the negative charge on the more electronegative atom or the positive charge on the less electronegative atom. So let's finish up with one last example here, and this is just another example of that rule. So in this case, we have our aldehyde again, but we've lost a proton, an H+, from the carbon adjacent to that aldehyde. So we have a minus charge there. So this is going to be type A, right? Because we have a non-bonding pair of electrons on an atom adjacent to a double bond. So we can move this pair down to form a pi bond, and these electrons can go up on the oxygen, and we can draw a new resonance contributor. It looks like this, now with the minus charge on the oxygen. Okay, so in this case, the minus charge is spread between the oxygen and the carbon. So our hybrid structure, or our true structure, could be drawn something like this. Right, we're going to have a partial double bond here and a partial double bond here, and we're going to have a delta minus here and a delta minus here, and maybe we could say a delta minus minus on the oxygen. So in this structure, the minus charge is spread between the oxygen and the carbon. It's dispersed or delocalized between those two atoms, but a bit more of that charge resides on the oxygen. Resonance is an important concept that we will apply over and over again in this class. So the more you practice, the more you'll feel comfortable with it, and the more you'll see all of the different applications.